Okay, great. So let's start review part of the solid state physics that I mentioned in the first lecture hour. That we will first, very quickly review the introduction to solid state physics 1. That I assume you already learned that in the past. But this is also a very important foundation for the later purposes. So the review part consists of mainly the crystal structures and the X-ray diffraction in solids, and the Bloch theorem, and the Fermi surface, the Bloch zone, and the free electron gas in metals. And finally, we will formally introduce the very important concept, which is the elementary excitations or quasi-particles. And that is the steps in between this introductory level of solid state and advanced level of solid state physics. Okay? So if you already learned much of the introductory level of a solid state, please try to be patient, and you will learn something more deeply, I hope, during this review processes. Okay, so let's look at the first part of the review, which is the crystal structure of solids and the X-ray diffraction in crystal, which is a very useful experimental technique to probe the the properties of the crystal in solids. And as I mentioned at the very beginning, the solid state system consists of many ions and electrons. They are periodically sitting on the lattice. For example, in the cubic lattice, where we have three unit lattice vectors A1 and 2 and A3 pointing to, say, x, y, and z directions, and those open circles represent the ions or the atoms on the crystal. And we could use the X-ray to actually probe the underlying structure of this crystal, but we'll see that in just a moment. But let's just define the lattice. Okay, so the electron number density, which occupied nearby all the ion sites, is actually a periodic function of this real space vector R, because it's as you can see very obviously that the electrons densities actually modulate periodically over the lattice structure. So if you take a measure of the electron density at position R, and it is going to be the same as if you translate this position by a lattice translational vector T, which is given by this linear combinations of three lattice vectors, capital A, little a1, plus capital B, little a2, and plus capital C times a3 unit vector. And this A and B and C with the capital letters represent the integer numbers. And so you simply just shift your point by integer multiple lattice spacing, and if you measure the electron density over there by shifting by a lattice translational vector, and you'll get exactly the same electron density there. And that is the property of this solid state system, that you are dealing with the periodic structures of electrons and ions, and everything is periodic. Okay, so that's a very important point of solid state, which differ from the other systems, which don't have the lattice structures. So we are dealing with lattice. So remember, there's always a lattice there waiting for us to actually solve. And we could also define so-called reciprocal lattice vector, which is in sort of a Fourier space or momentum space. And the reciprocal lattice vector is defined by, again, integer multiple of a linear combination of the three reciprocal lattice vector B1 and B2 and B3, where B1 and B2 and B3 are defined by this form in relation to the real space lattice vector A1, A2, and A3. So many references or textbooks, this is called K-space vector, unit vector. K refers to the momentum space, and we will see that in just a moment. So the word reciprocal refers to the fact that it is kind of inverse of the real space lattice vector, because if you take a dot product between this, say, the Bi and Aj, where Aj refers to this A1, A2, and 3 real space unit vector, then you get the delta function times 2 pi. So it's kind of reciprocal to each other. The real space lattice vector and the reciprocal lattice vector are reciprocal or conjugate to each other by this normalization condition here. And another important meaning of this reciprocal lies in the fact that they kind of are related by a Fourier transformation, because the real space function can be converted by a Fourier transformation to the K-space representation of the same function. Okay, so that's the Fourier transformation of this electron density function n of r in terms of the Fourier sum of the electron density in a reciprocal lattice space, and G refers to the this reciprocal lattice vector G, which is linear combinations of this three unit vector in reciprocal lattice space. Okay, so this is nothing but the Fourier sum or Fourier integral, and the real space electron density function is kind of a linear combinations of all Fourier series of the reciprocal lattice density. And this Ng in the reciprocal lattice space is given by the inverse Fourier transformation of this real space electron density n of r. And of course, the phase factor is exponential to the I times G dot r is simply just the Fourier phase. Okay, so if you remember your applied math at your undergraduate level, you must remember this Fourier sum or Fourier series or Fourier integral. So this is exactly that. Okay, so why am I doing this? It's because these are the basic quantities that in the solid state physics that you should remember. And number two, it is because they are important to describe this elastic scattering of the solid state system. So imagine that I send in some X-ray, which is some kind of high energy, say, particle or X-ray beam, and I try to hit this target by the X-ray, and then the X-ray is going to hit this all these atoms and ions in the material, and then it will get diffracted. Okay, diffracted, and by an angle, say phi here, and then I can collect all this outgoing X-ray particles, and then I could just use a detector to collect all this amplitude and the scattering cross section and so on with respect to all this different momentum and also angles and so on. Okay, so during this scattering processes, those X-ray particles don't decay to other particles, and so their momentum actually are conserved. Therefore, this incoming momentum k with the magnitude k absolute value is actually the same as this k prime absolute value after the scattering. So this is called momentum conserved scattering or elastic scattering. So of course there are examples of inelastic scattering where some additional particles or dissipations occurred during this scattering processes, but we don't discuss this inelastic scattering at this point. We only restrict our discussions to the elastic scattering. So also there is a phase difference between the incoming and outgoing electron. So this, this plane wave like object mimic the incoming wave function of this X-ray particle. And this e to the I k prime dot r represents the outgoing wave function of this X-ray. So you could use a detector to actually collect all this outgoing, particles, and you could measure the scattering amplitude, or the amplitude, or the square of the scattering amplitude represents the probability of this scattering event to occur. Okay, so let's just try to calculate this scattering amplitude of this elastic scattering, and that is proportional to the outgoing wave function of that X-ray particle. So you could simply just collect all this kind of a phase difference multiplied by this, electron density operator. Electron density at any given positions in the solace, and you simply just integrate over the entire space of that objects. This is your target material. And when you multiply this electron density by this phase difference, you could actually define this delta k as k minus k prime vector, and then you could simply just use the definition of the reciprocal lattice vector, that this the Fourier transform of this electron density in the reciprocal lattice space is given by that formula, where you have this extra e to the I g dot r phase vector appearing here when you perform the Fourier transformation of real space electron density function. Okay, but this is kind of oscillation function of R, and is 0 in many cases unless there is a special condition is satisfied, and that special condition is when delta k is precisely this reciprocal lattice vector G. Okay, so which means that when this cancels, when this stuff in the bracket get canceled exactly, then you get simply just a number which is 1 in that integral, and then this is certainly a finite value. But if G is not exactly canceled by delta k, then you get the oscillation of this integral, and by the symmetry argument, when you simply integrate over the entire space of this target material, you get cancellations of all these positive and negative values, and therefore it vanishes. So, and this leads to the very important so-called Bloch condition, or elastic scattering condition, that delta k should be equal to the reciprocal lattice vector G in order to have the finite contribution to the scattering event. And you could rewrite this condition in terms of the square. You square this equation, and then you could simplify this condition, and this reduces to 2 times k dot g is actually equal to g squared. Okay, so in other words, sometimes you could use that k equals to plus minus half of g as your Bloch condition, or elastic scattering condition. So the Bloch zone and these Fermi surfaces are determined by this Bloch condition, which we will discuss in just a moment. Okay, so this Bloch condition is a very fundamental and important properties of periodic structures of solids and in terms of electron density function. Okay, so let's take a short break. When we come back, we will review another very important subject, which is Fermi surface, Beryllium zone of ordinary metals. Okay, so let's take a short break. Let's move on to the second subject of the review of an introductory solid state, which is the energy band and Fermi surface in ordinary metals, or a weakly Coulomb interacting electron system. So here is the cartoon picture of the metals in these crystal structures. Say to simplify this system, we consider just a one-dimensional array of ions and surrounded by free electrons. And remember, those electrons and ions are interacting by attractive interaction, which we already mentioned, the electron-ion potential. So the orange curves represents the periodic potential, which is between electron and ions, and which will attract those electrons surrounding by a particular ion position. We can consider all these electrons just living in the neighborhood of particular ions subject to this attractive electron-ion potential, and that's constitutes so-called a cartoon picture of the ordinary metals. Of course, the electron can hop from one side to another side, and in that case, electron can actually move across the different ion positions, and they may form energy bands and these metallic transport properties. But quantum mechanically, we should still want to understand how that happens. Okay, so this simplified cartoon picture actually leads to the very important concept, the consequence in solid state systems, especially for metals, is that all the electron states of solids could be divided into different energy bands, and energy bands are nothing but collections of different possible electron states where the electrons could populate in that states. But from, say, your high school, you know that insulators are the systems where the electrons fully occupied a particular valence band, so that electrons have difficulty transport to the other states because there is the energy gap between this valence band and conduction band. But if electrons only partially occupied the energy bands, and those electrons occupied those top energy levels could actually very easily get excited to the nearby higher energy states, and therefore the electrons can transport without much trouble, and that is the mechanism for the metals, ordinary metals. And the fully occupied valence band will only lead to the insulating behavior. So that is well known, but we should really dig into the deeper understanding on why that happened, how that happens. Okay, so we know the basics is that electrons can interact with Coulomb, and this Coulomb could be the force between two electrons, or one electron and one ion, and also between two ions. Okay, so this simple-minded Coulomb interaction, how come this could lead to this very complicated, say, formation of the energy bands and the different conducting or insulating behaviors of solids, depending on whether these electron states are fully occupied or partially occupied. So how come this simple-minded picture will lead to such a important consequence in solids? So that is the key point that you should understand. And if you have not, and you should go back to your introductory level of solid state. For example, the Ashcroft-Mermion chapter 9, or Kittel's first book, introductory level of the solid state, chapter 9. And there you will see something like this, and more detailed derivations of the formation of the energy bands and also the Fermi surface. Okay, so the underlying physics here are twofold. Number one is we have a very important theorem called the Bloch theorem in solid state, and because we have a periodic structure of electron and ions and also those potentials, and so for electrons, sitting in a periodic array and influenced by a periodic potential, say U, which is between electron and ions, for example. And this automatically, by Schrödinger equations or by quantum mechanics, will lead to the energy bands. And this is something that we will review. Okay, so this cartoon picture will lead to that profound consequence in solid state, and that is something that I hope you will gain more understanding from this lecture. Okay, so the Fermi surface is a geometry in this momentum space, or kx, ky, kz space, or reciprocal lattice space, with a constant energy, which we call mu f, and that constant energy is not arbitrary constant, but a particular constant, which we call this Fermi energy, mu f. And that Fermi energy corresponds to the total electron numbers that are occupied, available states below that energy. So if you sum over all the occupied states with the energy epsilon, which is less than or equal to this mu f, and you get a total number of electrons, which means that this energy, mu f, records the highest energy, populated by the electrons, and below which all the electrons are occupied, and above which all the electron states would not populate in that states, the conduction band, for example. And so all the states above this mu f become empty states, and all the states below this mu f are fully occupied. And if you simply just count, the number of electrons populating below the Fermi energy, and apparently when you sum over all the energy levels, by Pauli principle that each energy level can only allow at most 2 electrons to populate, right? So when you sum over all these occupied states, you get total energy levels that are fully occupied, and you multiply this number by 2, you get total number of electrons. Okay, so that comes from the Pauli principle that each energy level could at most populate 2 electron states with opposite spins, and the number of energy levels multiplied by 2 is equal to the number of electrons populated in those states. And therefore, the Fermi energy corresponds to the top energy level that electron populates, and below which all the states are fully occupied, and above which they're empty. okay? And this corresponds to the total number of electrons or total number of, occupied states. And, the geometry in the K space, with a constant energy mu f, define the Fermi surface. The Fermi surface is actually is topologically non-trivial in different systems. So we will, take specific examples of different geometries of Fermi surface in the later part of the lecture. Okay, so that's number one important, missing link is that we need to actually understand deeply, how this cartoon picture will lead to that important consequence in solid state. So that's number one thing that we should review. So we will come back to the Bloch theorem and this periodic potential and the formation of energy band and so on. So this energy gap is actually proportional to this potential, the periodic potential. Okay, so the second thing that I would like to remind you is the definition of the Bloch zone in solid state, which I believe most of you or all of you have learned that in the introductory level of the solid state. So, for example, in this two-dimensional lattice in the K space or reciprocal lattice space, we could define the reciprocal lattice vector G of the nearest neighbor, say K point, G1, or the diagonal points, which we call this G2, or the second neighbor points, which we call G3. Okay, this is the G1, G2, and G3 follow the same definition that we defined earlier, the reciprocal lattice vector. So the Bloch zone is the area in the K space that is enclosed by perpendicular bisectors of those G vector, G1, G2, and G3. So, for example, the first Bloch zone is formed by connecting all these dashed lines which cut this G1 by half, but you should connect all different dashed lines which are this perpendicular bisector of G1 along these four different directions, and therefore the first Bloch zone is perfectly a square. Okay, indicated here. And so this is just a simple square lattice, but you can imagine that this Bloch zone could be more complicated geometry in different lattice structures. And the second Bloch zone, again, is a triangle like this. There are four triangles. Again, so these triangles are made by connecting this perpendicular bisector of the G2 vector. So you could imagine that I have three different orientations that I could cut this G2 by half, and then you connect all these three dashed lines, you can find this triangle like this. Okay, so again, you could do the same thing to form this third Bloch zone by connecting this perpendicular bisector of the G3, which is this horizontal line here, and you could imagine that you should exclude all this first and the second Bloch zone, and the remaining geometry is actually the shaded area by blue, which is the third Bloch zone. So there are many little triangles here. So the Fermi surface for free electron gas in the continuous limit where this lattice spacing approaching zero is simply a circle, right? So because you could very clearly see that this condition to have a constant energy for free electrons, which carry only connecting energy. So I suppose you already learned that in quantum mechanics. So this is simply just proportional to connecting energy, which is a constant. And the kinetic energy is nothing but 2m in the denominator and px squared and py squared in the numerator. And you could you simply just add this kinetic energy along 3 different directions. You get a total kinetic energy. The free electron don't have Coulomb interaction at all, so you simply just don't care about this potential and consider just sum of the kinetic energy, and this leads to this kx squared plus ky squared equal to the constant, and that constant is proportional to the Fermi energy. All right, and the geometry of this free electron gas in 2 dimensions is certainly a circle in a continuous limit where we don't consider a lattice for the moment. And you could very easily just map out all this Fermi surface in the reduced Brillouin zone scheme, which means that the first Brillouin zone, the Fermi, the occupied states within the Fermi surface form a square, and the second Brillouin zone with the occupied states within the Fermi surface is the shape shaded by the blue, and again the third Brillouin zone with the occupied states indicated by this shaded orange. So that is simply just the sort of a simplified version of the Fermi surface for free electron gas without the limit. Sorry, in a continuous limit without the lattice. But on the realistic lattice, for example, the square lattice, the geometry of the Fermi surface is not a circle but a diamond shape. For example, for a time binding electrons on the square lattice, you could check your Oshkov-Mermian details for a tight binding model of metals, and you could obtain this dispersion of the electron excitations, and that constitutes the sum of the cosines along x and y direction in 2D. So if you consider the half filling of this band, and you could easily see that this diamond shape is the Fermi surface corresponding to the half-filled electron band of the time-binding metal. Okay, so it's not a circle, but a different geometry in a realistic lattice case. But this is something that you need to review and you need to understand better, right? So let's take a short break. When we come back, we will go back to this, the first cartoon picture here, that's the periodic potential plus the Bloch theorem will lead to the energy band and an energy gap. Okay, so let's take a short break. So let's continue. As I mentioned, we need to understand better and more deeply how the periodic structures of these electron ions will lead to the energy bands and the Fermi surface and so on. Okay, so but to understand this, we need to go back to basics, which is the Bloch theorem for the eigenstate of one electron Hamiltonian under periodic potential, with the Hamiltonian defined as this one, where this gradient square term represents the kinetic energy of a single electron, and this U of R represents the periodic potential, which is the same if you simply just shift this R by a lattice vector. So for all such lattice vector R on this Bravais lattice, which are simply just a standard kind of say, for example, cubic or FCC or BCC kind of a lattice. So the eigenstate psi in such a system could be chosen to have the form like this. All right? So the eigenstate of that single electron under the periodic potential is given by e to the I k dot r times the function, which is the periodic function u and k as function of r where if you simply shift this r by, again, the lattice translational vector, then you go back to this UNK again at position r. So this is highly non-trivial. And in particular, if you simply just shift this eigenstate or wave function by, again, the lattice translational vector capital R, then you get this extra phase factor e to the ik dot capital R multiplied by this psi at this little r. So this is really, remarkable and fundamental and highly non-trivial. Okay, so this is called Bloch theorem. And for those of you who are not familiar with the Bloch theorem, well, you need to get familiarized with yourself this Bloch theorem. So in other words, the eigenstate of that single electron under the periodic potential, by shifting this lattice translational vector, carries the extra phase factor e to the ik dot r, capital R. So that is something very fundamental and very useful to actually derive this energy bands and so on. So there are some remarks that I need to make here regarding this Bloch theorem. By the way, you could go back to Ashcroft-Fermi in chapter 8 to review this Bloch theorem. So the remark number one is that the wave vector k is not identical to the electron momentum. Remember, in the free electron gas problem, so this k is actually proportional to this momentum, but under its periodic potential, so this lattice wave vector k is not identical to the electron momentum, which is minus h bar gradient of this wave function. So the reason is that if you simply take the gradient of the wave function and under such a Bloch theorem, you get extra term. In addition to this so-called crystal momentum h bar k, you get an extra term. So if this u nk of r is simply just a constant independent of a position, then this gradient term vanishes. Then you go back to this simple interpretation of this k, which is your electron momentum. But under such a Bloch theorem, you cannot simply identify this wave vector k as the electron momentum because there is an extra term. This extra term involves the periodic, non-trivial eigenfunction u and k of r over there, which we will derive later, right? But I will assign, the proof of this Bloch theorem to you as a homework exercise. Okay. So number two is that the k, this momentum, the wave vector k, is confined in the first Bloch zone. It's called the reduced Bloch zone representation. And number three is that this label, this end labels the different solutions to the Schrödinger equation for the one electron system under periodic potential, and this is the Schrödinger equation, or eigen equation. If you plug in this, say, this Bloch theorem back to this Schrödinger equation for that one electron, and this is the eigen value problem that you need to solve to get this UK of R. And you will see immediately that this solution UK of R is actually, there are quite many. In fact, there are infinite number of solutions which will satisfy this U of K, and we can label all this end, where n goes to infinity, and different, say, eigenstates which are solutions of this Schrödinger equation. And we will go back to this later. And number four is that this velocity of Vn of k is defined as the gradient of your energy, excitation energy, divided by h bar, which measures the mean velocity of electron. Okay, so let's come to the proof of this Bloch theorem. which constitutes a very important fundamental theorems in solid-state physics, and which I believe every one of you should understand deeply, 100%. Okay, so I only sketch the two different ways to prove this Bloch theorem. The first way is by the so-called translational operator, capital T of R in quantum mechanics, which is an operator, and when you apply this translational operator on any function f of r, say this f of r could be a wave function, okay, and then this f function, the argument inside this f function automatically shifts by this vector r. So that's something that we mentioned over there when we define the solution of the Bloch state. And you could use this kind of a translational operator, capital TR, and to show that this Hamiltonian is actually invariant under such a unitary transformation of this translational operator TR HTR inverse. If you simply just combine the three operator and you go back to your Hamiltonian H. Okay, so that's the first route to show this Bloch theorem, to prove the Bloch theorem. The second way to prove the Bloch theorem is by directly solving the Schrödinger equation for that single electron under a periodic potential, which is given by this Fourier sum of this periodic potential, U of r. And you could Fourier transform this eigenfunction or a wave function psi of r, and you can also Fourier transform this periodic potential in a reciprocal lattice space, capital K, and you could plug in this kinetic energy in K space and potential energy also in K space, and you could write down this eigenvalue equation by plugging this potential and kinetic energy to the Schrödinger equation, and this is the equivalent eigenvalue equation that need to be solved if you plug in the single electron wave function to the Schrödinger equation. And this is, remember, this is sort of a single particle quantum mechanics, but under the periodic potential. So in some way, this is still a single electron quantum mechanics, but in other sense, this is kind of going beyond the single particle picture because you have a periodic potential over the lattice, and you could solve this eigenvalue equation to get the Bloch states defined over there. Okay, so this is your first set of a homework problem. So I assigned these two ways to derive this Bloch theorem to you as a homework problems. Homework number 1, use the translation operator to prove the Bloch theorem. Number 2, homework is to again solve the Schrödinger equation for that single electron under periodic potential by solving this eigenvalue problems restricted to the first Bloch zone, where you could define this little q as a little k subjected by this capital K, and you can shift this capital K prime by capital K. And again, the second approach is by solving the Schrödinger equation in momentum space, and you simply just need to solve this equation. All right? So, but again, some derivation already there in Oskar-Mermian chapter 8, so you could go back to the Oskar-Mermian. So it is a very good opportunity for all of you to get familiarized the Bloch theorem. And the solutions are there, but do not just copy the textbooks. derivation. So use your own words and use your own way. And when you read this, Ashker-Mermian chapter 8 on Bloch theorem, try to understand. Instead of simply just going through this equation line by line, but think about this physically. So what is the meaning of this extra phase factor e to the I k dot capital R? What is the correct interpretation in terms of physics? So why is the fact that on the periodic potential, electron eigenstates will carry such a phase factor? Okay, so why is this eigen function u and k is also translational invariant? Okay, so everything is affected by this periodic potential. So that's what I'm emphasizing, many times, that in solid state we are living in a world of a periodic lattice with a periodic potential. So everything is periodic. So go back to Ashker-Mermian chapter 8 and try to use your own words to derive the Bloch theorem and understand 100% the Bloch theorem, what it means, and what it implies, and what the consequence of Bloch theorem. Okay, so let's take a short break, and when we come back, we will continue the review. By following the Bloch theorem, we could show that the electron states form energy bands under such conditions. Okay, so let's take a short break. So let's continue, but due to the time constraint, we can only sketch the derivation of this energy gap from the Bloch theorem today, but we will give you detailed derivation next time. So the next topic is the electron in the weak periodic potential, which will lead to the energy bands, okay, by Bloch theorem. So the way that we derive such a energy gap in the electron excitation energy spectrum in terms of this momentum little q is that we, again, as I mentioned, this is the second route to prove this Bloch theorem by Fourier transforming the eigen state or eigen function of that electron back to the Schrödinger equation, and also we Fourier transform the periodic potential in K space, and so we solve this eigenvalue problem, solve this Schrödinger equation for that single electron, and after solving for this eigen states and especially the eigen energy, and we finally find that this epsilon is given by this two branches, where epsilon 0 as function of q is actually the free energy, kinetic energy, the free electron kinetic energy, and this plus minus square root of this square plus square is the special features because of this periodic nature of this potential. Okay, so next time we will start from the Schrödinger eigenvalue problems, and we try to derive the excitation of the single electron under such a periodic potential by Bloch theorem, and we'll derive that the excitation energy of a single electron splits into this lower band and this upper band, and the lower band is sometimes called the valence band, and the upper band is called the conduction band. And these two bands separated by energy gap, which is the order of u of k, and that is the source of the energy band. Okay, again, the Bloch theorem is the heart and is the core of this band structure or the energy bands in solids, and we will go through some details next time. Okay, so I'll see you, next time.